Hello, welcome back. This is solving for case 2 of our kinetic friction problem, kinetic rigid body friction problem. And case 2, we just solved for case 1 in the last video, and we determined that friction was not working, meaning that the friction needed to roll without slipping was larger than the maximum allowable friction, which is static friction. That tells us that case 2 is the correct case. And case 2 is slipping. Now with slipping, we know what's going to happen is friction is known because friction is going to be in that kinetic friction region. If you remember the graph of friction, when you start putting a load on, friction meets it till it gets to the maximum static friction, then it drops down. And we're looking in this area over here where we are in the kinetic friction region, which is mu k times n. So we know the value for friction. It's as if friction is a given in this one. Friction is equal to mu k times n. Now if you remember, we solved for n in the last problem. I'm just going to go ahead and do it again. And once we have n, we have f. There's always a check to every case. Now we know this is the correct case because we solved the other one. But if you had done this case first, you would want to check that your AGX would end up being less than your alpha r. Why is that? Because you're going to get a larger alpha. When it slips, it's going to be able to have a larger angular acceleration than it would if it didn't slip. So we will end up checking that at the end, just in case you did case 2 first. Let's go ahead and solve for this. We could use the kinetic diagrams, but if you remember when I did the sum of the moments about point A, friction fell out entirely. Friction wasn't even a part of it, and we want friction because it's a known. So we might approach this one a little differently and say, let's do sum of the forces. We'll use sum of the forces in the x direction is going to be equal to mass times acceleration of the center of mass in the x direction. If we look at all the forces in the x direction, there's only one, and that's friction, and it's pointing in the negative direction, so we get negative F is equal to mass, which is 100 kilograms, times the acceleration of the center of mass in the x direction. We have two unknowns, friction and acceleration of the center of mass, but as I told you a minute ago, friction is in the kinetic region, so we can plug that in. We know that friction is going to be equal to our kinetic friction, which is going to be mu k times n. So if we know n, we know F. We're going to jump to sum of the forces in the y, just as we did in the last problem to find n. And none of this is different from the last time we solved it. If you had it on your paper, you could just repeat that same information. I just erased it, so I'm going to do it again. We know the acceleration of the center of mass in the y direction is 0. The forces in the y, we have 3 of them. We're going to have P, we're going to have W, and we're going to have N. 2 of those are pointing down, one's pointing up, all equal 0. So that tells us that N equals P plus W. Those are both known. 500 newtons plus 981 newtons. That's just 100 kilograms multiplied by 9.81. So we know that N is 1481, just as it was when we were solving case 1. So that means that friction is equal to 0.15, which is that mu k, times 1481 newtons, which is equal to 222 newtons. Okay, so we now know our frictional force. We can plug that into our equation right here, and we can find AGX. We get negative 222 equals 100 times AGX. Solve for AGX. AGX equals negative 2.22 meters per second squared. Okay, so just like that, we got an answer of AGX. Now we need to figure out how we can relate that to alpha. We could go back if we wanted and do the kinetic diagram like we did in the last one, or if we had already done that, we could use that equation. In this case, I think I'm just going to do some of the moments about point G so that we can find IG alpha. So we'll use some of the moments about point G is equal to IG alpha. And if we look at the moments about point G, we have F and we have P. are the only two things making a moment about point G, and we know both of those. If I put my thumb on G, I put my fingers out, P is going to be a positive, so we'll just say P times 0.3 meters. Same thing with F. F will be a negative. If I point my thumb out, fingers towards F, it tends to bend it back, and I'll have negative F times 0.15 meters. Those are some of the moments. That's going to be equal to Ig alpha. Notice here that I'm not using the equation Ag equals alpha r. It's not true when they're slipping, so we can't use that for case 2. Okay, I'm going to go ahead and plug in P and plug in F. So we end up with 150, which is 500 times 0.3, 150 Newton meters, minus F is 222, 222 times 0.15 Newton meters equals, I'm running out of room here a little bit, Ig, we did that in the last slide, the last video as well, where Ig is equal to m kg squared, which equals 100 kilograms, 0.2 squared, which is equal to 4. And the units are kilogram meter squared. We can plug that in right down here. That's going to be equal to 4 alpha. Okay, I'm just going to move over here so I have a little bit more room. I can solve for alpha. Alpha is going to be equal to 150 minus 33.3 over 100, over 4. Yeah. And if you do that calculation, that's going to end up with 29.175 radians per second, which is equal to 29.2 or close to that. We'll do 3 significant figures. Okay, at this point we know that this is our correct answer because we have already done case 1. We know alpha is equal to this and AGX is equal to negative 2.22. But let's just make sure that it makes sense to us. Remember in the when we solved case 1, we had an AGX of negative 3.6. So this AGX is less, meaning it's moving less quickly to the side, to the negative x direction. We also had an alpha of 24. We have a larger alpha now of 29.2. Because of the slipping, it's able to have a larger angular acceleration. Okay, so this makes sense to us. These look like the right answers. If you had done case 2 first, which you could have done, that's a perfectly valid way of solving it, you would now need to check to see if case 2 is valid. How would we do that? Well, we look at AGX, negative 2.22, and we say it has to be less than alpha r. Let's check that real quick. Alpha r would be 29.2. R is 0.15. You calculate that together. This is our alpha r. Looks like I didn't do that one. So 29.2 times 0.15. We get 4.38. And we can see that our AGX, I'm sorry, we get negative, oh no, we get alpha is positive, AGX is negative. Yes, I should have a negative sign on here because of the, just like we did in the last problem, if I have a positive AGX, I expect a if I have a positive alpha, I expect a negative AGX. With that negative sign on there, I can see that 2.22, which is our AGX, negative 2.22 is less than negative 4.38. Or 2.22 is less than 4.38. The negatives made it confusing in there because a larger negative number is actually less than. Hopefully that makes sense to you, and you can see that if you had done case 2 first, you could prove to yourself that case 2 is valid. If you found that this wasn't true, then you'd have to go back and solve for case 1, and case 1 would be the valid one. Hopefully this was helpful. Let me know if you have any questions.